Modern engines are perceived to fail faster than older ones, primarily due to increased complexity, stricter emissions regulations, and design choices that prioritize efficiency and cost over extreme longevity. These factors lead to more fragile systems that are sensitive to maintenance and prone to expensive repairs. Number 8. Increased complexity and more components. Internal combustion engines of today are extremely complex electromechanical systems that frequently integrate hundreds of interdependent subsystems and parts. Today's engines rely heavily on electronically controlled fuel injection, variable valve timing, turbocharging, sophisticated emission control devices, and dozens of sensors that are constantly in communication with multiple control modules, in contrast to the mechanically simple engines of the past, which were mainly composed of pistons, valves, carburetors, and simple ignition systems. Potential failure points are added by each component. For example, irregular engine behavior or shutdown may result from a malfunctioning camshaft actuator or a defective crankshaft position sensor. Because software control is integrated, even little errors in ECU programming or distorted sensor signals might have serious mechanical repercussions. This intricacy raises the possibility that otherwise minor issues with electronic modules or actuators can result in expensive failures that can limit engine life, since it necessitates sophisticated diagnostic tools and specialist repair knowledge that were not required for prior engines. Number 7. Turbocharging and higher mechanical stress. Modern engines now experience far higher mechanical and thermal stresses as a result of the widespread use of turbocharging, which involves pressurizing intake air to boost power and efficiency from smaller engines. By forcing more oxygen into the combustion chamber, turbochargers allow for tighter air-fuel mixes and higher compression pressures, which raise cylinder pressures and peak combustion temperatures. Critical parts including pistons, piston rings, cylinder walls, connecting rods, and bearings are subjected to fatigue damage and thermal deformation more quickly under these circumstances than in naturally aspirated engines from previous eras. Furthermore, oil coking from neglected maintenance, such as infrequent oil changes, can result in premature turbo failure and subsequent engine damage. Turbochargers themselves are made up of rapidly spinning turbines and bearings that operate at extremely high temperatures and RPMs. Larger displacement engines that are naturally aspirated have historically produced their power with lower internal pressures and temperatures, which led to less aggressive wear rates and frequently longer service lives. Number 6. Stricter emissions regulations and additional systems. Modern engines have many auxiliary systems, including diesel particulate filters, exhaust gas recirculation, selective catalytic reduction, and advanced evaporative emission controls, to meet strict international emissions regulations. Although these technologies significantly lower pollution, they also add complexity and new maintenance failure areas that shorten engine life. To reduce combustion temperatures, for instance, EGR valves recycle exhaust back into intake air. However, they can clog with carbon deposits, limiting airflow and leading to stalls or rough running. Diesel particulate filters collect soot particles, but they need to be actively regenerated at certain temperatures. If these temperatures are not met or the drive is not done frequently, the filters may become clogged, increasing back pressure and putting stress on the engine. Number 5. Use of lightweight and cost-effective materials. To meet stringent fuel economy and environmental targets, manufacturers increasingly engineer engines using lightweight materials such as aluminum alloys for blocks and heads, magnesium or plastic for intake manifolds and valve covers, and composite materials in ancillary systems. These materials reduce overall vehicle weight and improve thermal efficiency, but often have thinner cross-sections and smaller safety margins than the cast iron blocks and steel components prevalent in older engines. Aluminum and other light alloys tend to deform or crack under repeated heat cycles and mechanical stresses more readily than heavier traditional materials. Number 4. Heavy dependence on electronics and software. Modern engines rely extensively on electronic control units that constantly monitor operating conditions via dozens of sensors, e.g. oxygen sensors, mass airflow sensors, NOx sensors, and dynamically adjust fuel injection, ignition timing, valve operation, and turbo boost. While this precision enhances performance and reduces emissions, it also makes engines vulnerable to electronic malfunctions. A damaged wiring harness, water intrusion, software bugs, or sensor failures can cause the engine to enter limp mode, shut down unexpectedly, or run inefficiently, accelerating wear. In contrast, older engines utilized mechanically simpler ignition and fueling systems, which could be inspected and repaired with fundamental mechanical skills and basic tools, contributing to their reputation for reliability and longevity. Number 3. Lower tolerance for maintenance, neglect. Older engines were characterized by robust, overbuilt designs, with loose mechanical tolerances and forgiving lubrication and cooling systems, which allowed them to tolerate irregular maintenance schedules without catastrophic failure. Basic lubricants and infrequent oil changes did not immediately jeopardize engine health. By contrast, modern engines contain finely machined variable valve timing mechanisms, high-pressure fuel injectors, and turbochargers whose components rely on high-quality synthetic oils, stringent oil change intervals, and clean filters to prevent rapid degradation. Neglecting these requirements causes accelerated wear through oil varnishing, sludge buildup, carbon deposits, and abrasive fuel residues. For example, oil degradation can cause turbocharger shaft bearing failures that quickly evolve into larger engine damage. This reduced maintenance tolerance means modern engines often face earlier failures if owners do not strictly observe manufacturer service recommendations and use high-grade consumables, unlike ancestors that could run dirty for longer periods. Number 2. Design priorities shifted toward efficiency and emissions. The fundamental focus of modern engine design has shifted toward maximizing fuel efficiency, reducing emissions, and meeting regulatory mandates, often at the expense of absolute mechanical robustness. Engines operate with lean air-fuel mixtures, highly precise ignition timing, and valve overlap optimized for combustion efficiency rather than simplicity and margin for error. This precise operation involves pushing components closer to their physical and thermal limits, such as running at higher peak cylinder pressures and temperatures, which can accelerate fatigue and thermal strain. Older engines prioritize overbuilt components, simpler fuel delivery carburetor, and less stringent combustion parameters, which allowed them to withstand variable operating conditions and abuse with lower risk of failure. Number 1. Cost and production pressures reduce durability margins. Automotive manufacturers face intense market competition and regulatory pressures to reduce vehicle costs and improve fuel economies without sacrificing performance. These pressures have led to adoption of cost-saving measures. Modern engines are often engineered to reliably operate only within expected warranty terms or ownership cycles, rather than designed for indefinite rebuilds and extended lifetimes. Repair complexity and integrated components discourage extensive rebuilding oftentimes. Engines are replaced as whole units rather than overhauled, and contrasting with older engines built with higher margins and designed to be repaired repeatedly. This strategic shift to cost-effective, disposable engineering results in engines that may perform well initially, but lack the longevity and resilience characteristic of older power plants. In summary, modern engines are often designed with a trade-off between performance, emissions compliance, and cost, which comes at the expense of longevity, whereas older engines were generally simpler, with heavier, more robust materials and less complex systems, allowing them to last much longer with basic maintenance. If you liked our video, please hit the like button and subscribe to our YouTube channel.